Hey everyone, today we're going to look at our last topic for the year, and that's going to be sound. And we'll use this as an opportunity to learn about something in physics called waves. So we're going to sort of use this as a format to look at this sort of different thing that we haven't really talked about yet. So what is sound? Well, sound is an example of a wave. So a wave is basically a way of transferring energy without transferring mass, and you can kind of think of it like think of a wave you're familiar with, like an ocean wave. It's this traveling energy. It goes from like out in the ocean, and then it like kind of travels along, and then eventually it hits the shore. So what a wave actually is, and we're really going to primarily focus on sound. It's like basically it's a traveling vibration of air. And that's what sound is. It's this sort of air that is vibrating or moving back and forth, and that vibration travels from one place to another. And that's how sound travels, from like a speaker to your ear, or if you're speaking to someone a long distance away, the sound travels like from you to them. So this traveling disturbance, this traveling vibration, that's what sound actually is. And again, you can kind of think of it like that ocean wave of, we have this vibration that's sort of traveling along the water. This is very similar to vibration that travels through the air. And so if you have something like a speaker, all it really does is it basically just pushes air forwards. So it kind of pushes air, and what that does is it creates like a bunch of air that's clumped up together. Sort of a nice way of looking at it is like this right here. So we've got, imagine this is like a speaker that kind of pushes air forwards, and what you're seeing is each time it sort of goes forwards, notice how like there's the quality is kind of in and out. Notice how we have these clumped together little parts of molecules, essentially what they would be, these clumped together disturbances of air. And that's what sound actually is. It's just these sort of clumped together disturbances that hit your ear, and your ear has like a way of registering that, and your brain interprets that as sound. So we have these sort of clumped together parts, or compressions of air molecules, and then these open spaces in the middle where the air is more spaced out. So if we were trying to draw it, again, all the speaker does is it pushes air, so you have like a bunch of air molecules really clumped together in one place, and then they're kind of spread out in the middle. And then they're really clumped together in another place. Let's get more clumps. And then they're kind of spread out, and then they're really clumped together, and you kind of get the idea. And that clumped together, that's like that's our disturbance that I'm talking about, and that is what sort of travels in space. And as those sort of clumped together parts hit your ear, you have this thing in your ear, and your eardrum, it basically just pushes that eardrum, that membrane that you have, and that pushing, again, like your ear has some organs inside of it, and a way of registering that disturbance as sound, and that's how you're hearing me right now. It's just that process. So a couple neat consequences of that. So why can't you hear a sound in a vacuum? You might have heard this before. There's no sound in outer space. So like I don't know if you ever watch like a Star Wars movie and there's an explosion and you hear it. That's not realistic. You would not notice that. You would not be able to hear that. Why not? Why is there no sound in space? Well, remember, kind of thinking about what sound is, it's a traveling vibration of air. That's what it is. It's that air hitting your ear that creates sound. So why wouldn't you hear it in a vacuum or like in outer space? Because, well, there's no air. How can this traveling air disturbance travel if there's no air? Like, it couldn't. It's not as obviously silly, but it's like asking, like, why can't you have water waves if there's no water? Because like that doesn't even make sense. How can you have water waves if there's no water? That's actually exactly what this is. You can't have sound without air, because that's what it is. Or number two, if you slow down time and looked at a guitar string after being plucked, what would you see? So what we're thinking about here is like what is sound? Like, what are instruments? How do they produce sound? What's actually going on here? So if you pluck a guitar string, you hear the sound for like a while, like it continues onwards. So if you were to look at it, and this one's like slow, this video we're going to watch is in slow motion quite a bit. If you strum a guitar string, notice that all of these, all the guitar strings continue to vibrate back and forth with like a certain frequency or a certain regularity. This vibrating back and forth, That's what produces these regular air disturbances. That's what produces these, again, these clumped together air molecules that travel and reach your ear. And as long as it's tuned correctly, then, that sound would be, pleasant for you to hear. So, what would you actually see after being plucked? It would continue to vibrate. And that is what continues to create sound. And again, those air molecules that are together, as they vibrate, they're going to travel outwards so that everyone in the immediate area can hear the guitar. But what makes one sound different from another? You can hear different notes, like there's high notes and low notes, there's loud noises and soft noises. What about this air, these vibrating air molecules, what creates that? Well, there's a few different things that we talk about when we talk about waves. We have frequency, amplitude, and then we'll talk a little bit about speed and wavelength as well. So, frequency. Frequency is the sound wave, is the number of vibrations per second. Oh, goodness. The number of vibrations per second. It's kind of what it sounds like. It's how frequently it occurs. So this is a value that we're going to talk about kind of continuing forward in the unit. It's measured in something called hertz. So this one you might have seen before, computer processing speeds, that kind of stuff. Frequency is measured in something called hertz. So as an example, if you have something that's 20 hertz, what does that mean? Well, that means that there are 20 vibrations per second. 20 vibrations per second. So when you see there's a frequency of 20 hertz, what that means is there are 20 different sound waves hitting your ear per second. And sometimes you'll have very high frequencies, you can hear hundreds of hertz. That means there are literally hundreds of these sound waves hitting your ear in 1 second. So when we talk about that unit, hertz, that's what we mean. It's the number of times this happens per second. And you can detect different frequencies of sound. Frequency is heard as pitch. Like a high pitch versus a low pitch. A high note versus a low note. That's how you detect different frequencies. A high pitch is a high frequency. So this is a really cool thing that you have the ability to do. And it's really cool if you think about it. Again, what sound is it's these air molecules hitting your ear. And a bunch of them hit your ear per second. The more hit your ear per second, the higher the frequency is, the higher the note is that you hear. So your brain has this way of taking this sort of very random piece of information, the number of sound waves per second, and turning it into pitch, which is the way that your brain sort of processes that information. Now, you can hear a frequency of roughly the range from 20 to 20,000 hertz. So a sound wave that reaches your ear about 20 times per second would be the lowest, deepest note or tone that you could hear. And at about 20,000, that's where the frequency is a little too high and you wouldn't be able to hear that either. So if you look at something like this is a tone generator, so this noise is going to be a little bit annoying. But if we start at 440 hertz, if you're familiar with, if you play an instrument or something like that, this is your concert A that you probably tune to. Oops. Okay. Feel free to turn the volume down as I go. Okay, so that plays a certain note, right? It plays this frequency. If we go higher in frequency, we'll notice a higher pitch. And then as we go higher and higher, we get a really high pitch. And I said about 20,000 is where you start dropping off. So if I play this 20,154, you probably won't be able to hear it. Because it's just too high, your ear isn't designed for it. And if I go down to roughly 20, you should lose the sound somewhere along the way as well. And so that's that frequency. That's what you're hearing. You're hearing this pitch. So it's a high note versus a low note. Okay, amplitude. Amplitude is the amplitude of a wave is the size of the wave. And there are different ways of measuring it, and it can be very complicated for sound waves, which is basically how big the wave is. Oops. And so for a sound wave specifically, the amplitude would essentially be the size of the vibrations. So if each air molecule vibrates back and forth like a lot, then it would have a large amplitude. If it only like vibrates back and forth like a little bit, like they don't move very much, we would say it has a smaller amplitude. And it's a little bit weird to measure that for sound waves, but that's kind of what amplitude means. You can hear different amplitudes as well, just like you can hear different frequencies. The amplitude of a sound wave is heard as the volume of the sound. So alright, volume / loudness. So, like when you turn up the volume on your computer, you are like increasing the amplitude of these vibrations. You're increasing the size of the vibrations. And so there's a speaker somewhere in your computer or your headphones, whatever you're listening to, that pushes sound waves back and forth. If you turn up the volume, it pushes them back and forth like really, really hard. It increases their amplitude. Okay, we'll talk a little bit about the speed of sound. So the speed of sound in air is roughly something in the neighborhood of 340 meters per second. Which is pretty fast. If you imagine a football field or a soccer field is about 100 meters, that means that in 1 second, sound can travel about 3.5 of those entire fields in 1 second. So sound moves pretty quickly. But it turns out that the speed of sound in air isn't really very quick compared to some solid materials, or we'll look at a liquid first, water. In water, sound actually travels even faster because it's a denser material. In water, it travels at about 1,400 meters per second. Which means we're looking at a total of 14 football fields in 1 second, if all of the football fields are made of water. It's a little shy of a mile per second. And then the speed of sound in steel, so if we move, again, steel is very dense, it's very hard, is about 5,100 meters per second, which is over 3 miles in 1 second. So the sort of the denser the material is, the faster sound travels. Our ears are designed to hear sound in air, which is what typically works for us. If you listen to sound in water, it does travel faster, but our ears aren't like really designed for that, which is why everything sounds kind of like muffled or not quite the same if you're underwater. And the last thing we used to talk about waves, we're going to do like a real quick look at this rather than a deep dive here. Wavelength is the other thing we used to talk about waves. It's exactly what it sounds like, kind of. It's the length. This is such a bad definition. It's the length of the wave. It's just how long it is. We use a Greek symbol for this. It's the Greek symbol lambda. So if you kind of look this up on your own, you might see this used as the symbol for wavelength. For sound specifically, the wavelength of sound is the distance between vibrations. So it's how spaced out they are, and we describe that as the wavelength. We would measure it in meters because it's a distance. And that's sort of the last thing that we use to talk about sound. So something with like a short wavelength would be like something like this. This is a wave, and you can see how like scrunched together it is. A long wavelength might look something like that, where it's like very spaced out. It's a long wave, it has a long wavelength. Alright, let's work with a couple of these ideas real quickly, and that'll be good for today. So we'll do 3, 4, 5, 6, and that'll be good. 3, you hear a mosquito flapping its wings at 600 wing beats per second. What is the 600 wing beats per second? Okay, the number of times something happens per second. I'm hoping that sounds a little bit familiar. That is the frequency, the number of times something happens per second. So a mosquito creates that buzzing noise, right? That like zzz that you hear. And that, because you can think of like that note that it's playing, or that tone that you're hearing, is a result of the frequency that with which the mosquito flaps its wings. Let's say you've got like a faster mosquito. This one's going to flap its wings at 800 wing beats per second. How would that sound different? Well, that's a higher frequency, and so that would be a higher pitch. So, this mosquito, that buzzing noise it hear, like that zzz, would have a higher pitch, like zzz. Oh god, sorry, I'm not a music teacher. Which I'd probably make it more annoying. Number 4, compare what you say in B as shown below, which has a larger amplitude. Remember, amplitude is the size of the wave. Which of these has like a larger size to it? I'm going to go with, B for this one. I'm going with B because see how it goes much higher and much lower than A? It has like a greater size. Which has a longer wavelength? For this one, I'm going to go with A. Because if I trace like one full wave for B, say we go up, we go down, we go here, this right here would be the wavelength, this length. Now if I do the same thing for A in a different color, we go up, we go down, we go back to where you started. Now this is a wavelength for A. It's much, much longer or spaced out. And that's what wavelength means. Alright, 5 and 6. You join the track team. You're lined 100 meters from the finish line. You see the starter pistol go off, and a short time later, you hear the starter pistol. How much time did it take for the sound wave to reach you? So if you, I don't know, if you're in track or cross country or something like that, maybe you notice this, like they have like this little like pistol, not a real pistol obviously, that they shoot off, and you can see it fired, and then you hear the noise later because it takes time for the sound to reach you. If you're 100 meters away, how much time would it take for it to reach you? Well, we're solving for the time, and here I gave you your equations. These should look familiar. They're from our first unit this year. We're solving for the time it took, and I think that the one that would help us solve for time is this third one down here. That's supposed to be a check mark. T equals d over v. Now the distance is 100 meters, and if you tried this on your own and you had trouble with it, it is because you had to look up the speed of sound from a little bit earlier. In air, sound travels at 340 meters per second, so pretty fast. Meters per second. And I should have done this earlier. If you do the math for that one, you get 0.29 seconds. Okay, is that a lot of time? No, obviously not. But again, it's not 0 times. So there would be this delay in the time it takes for sound to reach you. And here's one that you can actually use. It's like the thing they tell kids and stuff like that. If you, you know how you see a lightning flash and then a few seconds later you hear it? Like there's a delay there. And what they sort of tell you is that for every 5 seconds that goes by, like if you see the lightning flash, you start counting. Like 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5. For every 5 seconds that goes by, the lightning is 1 mile away from you. And we can calculate that and see how it goes. So you see a lightning bolt, you count 5 seconds to hear the thunder. So you see the flash, and then 5 seconds go by, and then you hear it. What distance away from you was the thunder, if it took 5 seconds to reach you? Alright, we're solving for a distance here, right? So I'm going to go with this equation right here. D equals V times T. Alright, V is 340 meters per second. And I'm just getting that from the speed of sound in air, which I told you earlier. We said 5 seconds go by, right? Okay, so we're going to multiply the two values because that is what the equation told us to do. That says 5s, 5 seconds, I'm sorry. So we're going to do 340 times 5 seconds, and I got 1,700 meters. So if you're trying to think about what that is, if you run track, maybe you're familiar with 1,600 meters is about a mile. And so 1,700 meters is right in the neighborhood of a mile. So, I don't know, something you can try. You see the lightning flash, and you start counting. If you hit 5 seconds, it's 1 mile away. So that's sound. Basically, the big idea here is that sound is a wave, and we use some of these characteristics to describe, what a wave is, frequency, amplitude, and all of that. So I just wanted you to get like a little bit familiar with those for today.